Uh-oh. Chris, what's on your screen now?
You are, Dr. Bob.
Okay. So whoever's talking, you don't have the gallery?
Nope, it's the gallery. It's all three of us. Sorry about that.
Okay, good. So are we going to start, or do you want to say a few words?
Yep, all you.
It's all me. Okay, let me share my screen. And so people are still looking at us. So we have Chris Kaspar, I'm Bob Field, and Alyse Handley here. And we're all associated with Cal Poly State University on the Central Coast in California. And two of us are in California, and Chris, of course, is in the theater with you. And so I'm now going to share a new share. Here we go. Are you seeing the video, the screen?
Oh.
What?
Yep, all good.
Yep, okay. So I'm going to start Doomsday for Dinosaurs, a melodrama in 4 acts. As a fiery asteroid approaches Earth in this unrealistic scene, a small mammal anticipates the imminent doom of his nemesis and says, this could be a blessing in disguise. Act 1 is setting the stage, and I will talk about 13 billion years of history of the universe and the Earth before the dinosaurs ever reigned our planet. Act 2, Alyse will introduce us to the characters in our melodrama, the reptiles, dinosaurs, and mammals. And then disaster strikes, and Chris will explain that to you in Act 3. And Alyse will come back with the surprisingly happy ending to our melodrama, as anticipated by our little mammalian ancestors. So the National Academy of Sciences says that the role of science is to provide plausible natural explanations of natural phenomena. The Cosmic Evolution Project that I run explores and explains the evolutionary history of the Earth and the universe. And the project conducts secondary research, and that's what my 2 students have been doing, and sponsors special events for current and future science educators. So I am a physicist. I'm not a paleontologist. Alyse is a marine biology major about to graduate, and Chris is a physics major. And we had some help from a science script writer, Eileen Woodward. And none of us knew that much about dinosaurs 2 months ago, and we've worked hard to put together this program for you and for our website. And our website is at the top of the page here. It's under construction, and it's our evolution website, and it's the dinosaurs page. And I want to give special thanks to the GEM Theater for sponsoring and hosting this event today. So 13.8 billion years ago, the Big Bang nucleosynthesis only formed hydrogen, helium, and a little tiny bit of lithium. But we need the building blocks of life, which include carbon, nitrogen, oxygen, sulfur, and phosphorus, and the building blocks of Earth, which include iron, magnesium, silicon, and also oxygen. And of course, many more elements are found in living things and in the planet, but those are among the most common. So where did all these things come from if we only had 2 to start with? Well, it turns out 100 million years after the Big Bang, the first stars began to make all the elements. And so I've color-coded in this chart all the elements in the periodic table and where they came from: large stars, small stars, neutron stars merging, things like that. So 4.5 billion years ago, the shock wave from a supernova explosion squeezed a cloud of gas and dust into forming the solar system, which evolved into the planets, the sun, the moon, asteroids, comets, and life itself. And here we are in the Goldilocks orbit, which is just the right distance from the sun for microbial life to arise, and then eventually everything that's come ever since then. So there was a catastrophe shortly after the Earth formed. The Earth was a very uniform thing from all these rocks coming together, but it was very hot, and iron melted and dripped down from the entire planet to the core and sank. When that falling iron also heated things up even more, and also radioactive decay of elements heated things up more. So we ended up with an iron core, a mantle, and an outer crust. And the Earth continues to evolve, which is why we have earthquakes and volcanoes to this very day. At this point, though, we did not have liquid oceans yet because the Earth was still very hot. The next thing that happened as one final insult, a Mars-sized planetesimal, that's like 1/10 the mass of the Earth, about half the diameter of the Earth, struck our planet. When the dust settled, the giant impact resulted in the formation of an outsized moon, which would play a major role in the evolution of life. The impact also tilted the axis of rotation of Earth, which gave us seasonal changes, which are so essential to producing a favorable climate. The first eon in Earth's history is known as the Hadean. Due to the hellish conditions on the surface, it ended with a late heavy bombardment by asteroids and interplanetary leftovers scattered everywhere by the gravitational influence of the outer planets like Jupiter and Saturn, pulling on each other and migrating to new locations. So the moral of the story that we're setting the stage for is that asteroids are not a rare thing. There's a lot of stuff flying around in the solar system, especially early on, and eventually it settled down. At the end of the Hadean, oceans and the first stable atmosphere formed, providing finally an opportunity for microbial life to form. So life did begin in the Archean eon nearly 4 billion years ago, and life may have its origins in the aftermath of an asteroid strike as well, which may have altered the conditions just enough so that life being fed by the rich organic soup that rained down from space as part of all these things coming down were the building blocks of life, and also organic materials upwelling out from the interior of the Earth, which was still very active and molten, as you can see from here. So the next major thing was a few billion years later, the Great Oxidation Event. The original microbes did not do photosynthesis, but they were relying on this dwindling pool of primordial organic molecules that were in this kind of soup-like material. So the ancestors of cyanobacteria, which you may know as blue-green algae, evolved photosynthesis to convert sunlight, water, and carbon dioxide into food, separating their dependence from this dwindling supply of other materials. The waste product of photosynthesis is a highly reactive and surprisingly toxic oxygen molecule. During the Proterozoic eon, about 2.4 billion years ago, this molecule, oxygen, doomed the previously dominant anaerobic microbes to a few places that were sheltered from all this oxygen. This set the stage for a high energy future for life on Earth for those who could manage the toxic oxygen molecules. So here is the 4.5 billion year evolutionary history of the Earth, divided into what the geologists see as 4 main eons: the Hadean that I've talked about, the Archean, this very long Proterozoic, which preceded the explosion of life in the Phanerozoic eon. And so I'm going to expand this Phanerozoic into the Paleozoic, the Mesozoic, and the Cenozoic. Today's story focuses on the rise of the dinosaurs through the Mesozoic era. And you can see that the biggest dinosaurs started rising in the Jurassic, which is why the movies were called Jurassic Park and so forth. And there were many extinctions throughout history caused by things like volcanoes and asteroids and whatever. The Ordovician wiped out 100 million years after they first appeared in the geologic record many of the trilobites. The Devonian wiped out many more and many fish. The Permian was the greatest and wiped out marine species, insects, amphibians, and all trilobites. But life has always survived these disastrous events. Alyse is going to talk about the Triassic, and Chris is going to talk about what happened at the border to the Cretaceous when so many other things happened. So 360 million years ago, some plants evolved the ability to produce lignin, a complex molecule that made their cellular stems much harder and more woody. Thus, the first trees evolved. And bacteria and fungus did not immediately evolve the ability to decompose lignin. So the wood did not fully decay, but got buried under sediments, eventually turning into coal, which is why it's called the Carboniferous Period. This lasted for 60 million years. This was before the Mesozoic and the rise of the dinosaurs. These were reptiles shown here. And eventually the mushrooms and fungi developed the ability to decompose lignin, and that brought a close to the primary formation of carbon. It was very good that the coal formations buried so much carbon dioxide and increased the oxygen content in the atmosphere, because we are high energy oxygen based animals. And well, when we burn coal, of course, we're putting a lot of that carbon back in, which warms the Earth back to the climate conditions it had hundreds of millions of years ago. The Permian Triassic extinction transition wiped out a lot of things, and it went on for about 1 million years. And we think it was volcanoes, but if you look in Wikipedia, they talk about a lot of other possible explanations under Permian Triassic extinction event. So scientists once thought that oil came from dinosaurs because it was found in Mesozoic era sediments alongside dinosaur fossil bones. Sinclair Oil, headquartered in Salt Lake City, Utah, dinosaur country, promoted this idea even when I was a child 50-something years ago. Sinclair gasoline stations were everywhere. I noticed in the movies, they didn't show Sinclair, they showed a Chevron station, I think. And they tapped into our childhood fascination with dinosaurs. The pumps said Dino Care, the stores were Dino Marts, the dinosaurs were at the World's Fair, and they were in balloons floating above the crowd. But sadly, the notion that petroleum or crude oil comes from dinosaurs is a fiction. It is the opposite. Petroleum is a fossil fuel derived from tiny marine organisms, not giant dinosaurs. 70% of the oil formed when dinosaurs ruled in the tropical Mesozoic era. Only 10% formed earlier, and only 20% formed later. As the oxygen was removed from the detritus, decomposition slowed. So it didn't all go back up into the atmosphere as carbon dioxide. Over time, the remains became covered by layers and layers of sand and silt, and the weight of all these sediments, as it piled up thousands of feet, produced the pressure and heat, which transformed these compounds into the hydrocarbons and other organic compounds that form crude oil and natural gas that we find so valuable today, and that also, unfortunately, influence climate change. And this geologic map of Texas shows the various periods. Eventually, we're going to put all these pictures and stories on our website. We're still working on that, though. So we have set the stage for the Mesozoic, and I'm not going to brief everything on this chart, but Alyse is now going to talk about the meet the characters.
All right, thank you, Dr. Field. So the Earth looked very different during the Mesozoic era. If you looked out your window, what would you notice? What plants or animals would you see? What temperature would it be? These conditions that we live in today are very different from what the dinosaurs experienced about 243 million years ago. On the largest scale, the continents as we know today did not exist during the time of the dinosaurs. During this time, all the land masses on Earth were assembled as one large piece called Pangaea. Pangaea will eventually split apart due to tectonic plate movements, but this will not happen until much later in time. Dinosaurs first appeared on Earth during the Triassic Period. which scientists label as 252 to 201 million years ago. This period began after a large extinction event called the Great Dying, which is super original, I know. This marked the end of the Permian period. The climate during the Triassic period was hot and dry. Most of the Earth was like a desert. There were no polar ice caps, and in addition, all the continents were connected, so there was not a lot of diversity in the climate. So I think the next picture that we're going to show here is just an example of what the Earth could have looked like at this time. It didn't look like this. This is a modern picture, but it's just a good way to picture it. Oxygen levels on Earth were also at a lower level at this time because the large extinction event killed off all the oxygen-producing plants. Dinosaurs existed during this period, but they did not become the prominent, successful animals that we think of today until the Jurassic period. So this next slide shows just the general overview in a cute cartoon way of the way that dinosaurs came to be. They came from reptiles way back millions of years ago and eventually led to dinosaurs, crocodiles, and birds. But we'll get to the specifics a little more later. So looking in depth at the evolution of dinosaurs on the next slide. So dinosaurs evolved from reptiles over long periods of time into what we think of today. During the early years of the Triassic period, large advanced reptiles called archosaurs dominated. However, archosaurs were not dinosaurs. And this is confusing because, again, some scientists are not original when they name things. The archosaurs consisted of both plant-eating herbivores and small animal-eating carnivores, and they had relatively advanced respiratory systems, which allowed them to evolve and thrive during this time of low oxygen. This group of reptiles, would begin to slowly turn into more dinosaur-like creatures when it split into two different groups, the Pseudosuchia and the Ornithoridia. These groups of reptiles were very similar looking, but they had one important difference, and this was their ankles. Pseudosuchia had more ankle mobility, as their ankles were on the side of their torso. Ornithoridia found that they had less ankle mobility and were more stable standing up. Pseudosuchia is a group of reptiles that would evolve to eventually become the crocodiles, which makes sense when you think of the crocodile's ankles on the side of their body, as shown in this next picture. From the group of reptiles, the Ornithoridia, we get the evolution of actual dinosaurs. So from this group, we get two separate types. These would be the bird-hipped and the lizard-hipped. So the bird-hipped dinosaurs had hips that allowed them to walk on their back 2 feet or be bipedal. A famous example of this would be the T-Rex, as we show here. The lizard-hipped dinosaurs had hip bones which made walking on all 4 legs much more comfortable. From these two groups, a vast diversification of dinosaurs occurred, as scientists have identified over 1,000 separate species of dinosaurs. These animals came in all different shapes and sizes, based on the area that they evolved in and the food that they ate. There is an extinction event that marked the end of the Triassic period and the beginning of the Jurassic period. This extinction event killed most of the large animals on the planet, but it did not kill all the dinosaurs. This allowed for dinosaurs to take over their habitats in areas that they did not have access to prior to this event, which helped lead to the diversification and growth into the type of dinosaurs that we think of today. So this picture on the left shows the 2 different types of hips that I just explained. We see on the top is the lizard-hipped, and on the bottom is the bird-hipped. And this just shows how very different their bone structure look like, which lets scientists separate them into these 2 groups. So during the Jurassic period, the temperature was a bit cooler than the Triassic, but it was still relatively hot, as there was a high amount of carbon dioxide in the atmosphere that trapped the heat in. There was also a lot more rainfall during this time, which aided in the growth of plants on Earth and helped fill the ocean basins. It was during the Jurassic period where we begin to see large plants evolving, such as ferns and horsetails. This abundance of plant matter allowed herbivore or plant-eating dinosaurs, such as the brachiosaurs, to grow to large sizes, evolving and diversifying. It was during the Jurassic period that dinosaurs ruled and truly became what we think of today. So this picture just shows some of the great diversification that we see. They all look so different, and they're also all very large during this time. This is why we hear so much about the Jurassic period and even watch movies about it. So dinosaurs were not the only type of animals that evolved during this time. It was also during the Jurassic period in which mammals first evolved, specifically around 178 million years ago. Mammals evolved from a group of reptiles called cynodonts, which had large jawbones, no external ears, and large teeth. During this time, mammals were more like reptiles than they were like our dogs and cats, or even us for that matter. But they did have some of the characteristics that allow scientists to label them as mammals. These characteristics have been passed on to all mammals, including us, and are having small bones in our inner ear that help us hear, evolving fur or hair to keep warm, and developing placenta to give live birth to their young instead of laying eggs. During this time, mammals were all very small, mostly mouse-sized, the size of about a house cat. This is because dinosaurs took most of the resources and acted as predators. So here at the bottom, we see what a typical mammal would look like at this time. Very small and looks a lot like a mouse or a shrew. And then on the right, we see a basic family tree of the mammal and their descendants. We start at the top with very ancient animals that we wouldn't see today, but you can see how it leads all the way down to the placentals, which is the most common mammal, like you and I, and also marsupials, which is like the koala. The next period of time in which the dinosaurs lived was the Cretaceous period, which spanned from 145 to 66 million years ago. It was during this time that the continents began to separate and shift into the positions we think of today, like we see in this picture and like we would see if we were flying in a plane. Because of this, the dinosaurs and other organisms were distanced from each other and exposed to new climates. This caused a huge diversification event, leading to the incredible diversity that we see in our museums, in our fossil records, as well as the large diversity of animals, such as mammals, lizards, and even plants. If you were to walk into the world of dinosaurs, you would see many animals of varying shapes and sizes. Some dinosaurs were massive, weighing as much as 6 elephants or 30 tons, and some would be tiny, like the size of a cat. Some would walk around on all 4 legs, and some would run around on 2. The diversity of dinosaurs was all because of their ability to evolve and adapt to their environment. There was enough food and space for all of these different kinds of dinosaurs until there wasn't anymore. So this slide I just really like because it shows the great range of diversity and growth that we saw as time progressed. So here we see the really early dinosaurs, very small, very few. We see the Jurassic period where they evolve into these large, huge creatures. And then the last, the Cretaceous, is where we really see that true diversity, all different shapes and sizes, some really big, some really small, but overall just a great show of diversity. So next, Chris will be taking over and talking about the disaster. I'm not going to go over all these notes, but these are just some of the main points that I hit on.
Thank you, Alyse. So let's take a step back. If the dinosaurs were doing so well and were so diversified and had dominated the scene for so long, what did they do to disappear? Why aren't more of them around today? Well, some of you might know the answer. A giant space rock flew straight for Earth 66 million years ago. But what did one measly 6-mile wide long asteroid do to the Earth? Well, the asteroid hit the Earth at a whopping 12 miles per second. That's 25 times faster than Superman going faster than a speeding bullet. If we count to 3, 1 1,000, 2 1,000, 3, the rock made it from here to Cedar City and back with groceries. So with all that momentum, it released the same energy as 10 billion atomic bombs used during World War II. Sorry, did I say 10 billion atomic bombs? Yes, that's over 1 atomic bomb for each human alive today. The impact obviously caused a great deal of destruction. The whole world felt the effects either directly or indirectly. So this used to be Earth 66 million years ago, and the asteroid hit right up here in what is now Mexico's coastline at Chicxulub. It hit shallow coastal waters. Now, a lot of things happened at the same time. The massive 10 billion bomb impact displaced so much water that it formed a tidal wave a quarter-mile high. It caused fires to pop up hundreds of miles away. So locally, it would have smelled a lot like cooked dinosaur. Had the asteroid floated through space just a mere 5 minutes later, the Earth would have had time to rotate, causing the impact to hit an ocean instead of nutrient-rich coastline. Slide, please. In the same way as bombs today, the asteroid displaced a bunch of air, causing a shockwave that incinerated plants and animals 1,000 miles away. Us in Panguitch, if we had been around 2,000 miles away, would have been hit by the air blast in mere minutes. Had hoodoos been around, they would have toppled right along over with many of our bridges. It also produced very high pressures, creating a beautiful display of quartz that instantly crystallized, as seen on the right. The shockwave reverberated through the Earth, causing earthquakes and disrupting volcanoes across the globe. The most famous of the erupting volcanoes is located in India. So this is the Deccan Traps. This volcano range had been erupting and spewing out CO2 into the atmosphere for 30,000 years before the big hoorah came and made this volcanic eruption much bigger at the exact time that the asteroid hit. The leftover rock of all this spewed out lava is the size of Texas. So this destruction is cool and all, but it only explains the deaths of dinosaurs relatively close to the impact or close to volcanoes. So let's talk about the impact itself.
Sorry.
The energy of the very large, very fast asteroid was converted into heat, which melted the crater, creating a huge hole. Meanwhile, the impact caused giant shockwaves to go through the Earth at the speed of sound, causing earthquakes and nudging volcanoes past the tipping point of eruptions across the globe. This is just like if you dropped your phone on the ground. It turns into shockwaves into the form of sound, and the bulk of the falling energy is turned into heat. Unlike your phone, instead of cracking the screen, the asteroid hit hard, and temperatures rose so much that it vaporized upon impact. The shockwave reverberated after hitting rock at different densities. The implosion caused the crater to collapse on itself and form different ridges. All of this caused the crater that we can detect below the surface at Chicxulub today. So here's a map of the gravitational anomalies underneath 65 million years of sediment. The white line shows the coast. Extra rock is in green, yellow, and red, and lack of rock is in blue. The asteroid came down and landed on Earth at an angle. So this is very important. The impact occurred at a 60-degree angle, which is precisely the angle to inflict the max amount of damage on Earth's life. So what do I mean by inflicting the max amount of damage? Well, an asteroid going straight down at no angle would kick up fewer rocks and release less gas. With these low-angle asteroids, tsunamis, fires, earthquakes, and all the like would have still occurred, but dinosaurs on the other side of the globe might survive. Instead, the asteroid hit Chicxulub, which is a sulfur-rich area in the Earth's surface at a 60-degree angle, which meant it kicked up rich soil to block out the sunlight with sulfur and carbon dioxide in the atmosphere. This caused a planet-wide, decades-long winter that the dinosaurs could not survive. So here's a little simulation. Hopefully we don't get an ad for Tom and Jerry. It's being played tomorrow at 3:30 and 7, by the way.
Are you seeing the video?
We are not seeing the video.
Okay, I have to do a new share.
So since dinosaurs were present on
Is that
all the
it?
continents, yep, we're good now. And if you could full screen for us,
What?
if you could put that in full screen for us, that'd be great. So since the dinosaurs were everywhere, how did all this kicked up sediment in the air make all the dinosaurs except land birds go extinct? Well, to visualize this, we're going to look at a simulation. There's a couple differences with this simulation and the actual asteroid. This is set on a modern Earth, and the impact is in the middle of the ocean. So, and there's also no impact angle. So with this, we're looking to get a picture of the impact. So here we're seeing the huge space rock and its shadow, likely coming from the asteroid belt, or maybe a chunk of a very large passing comet. So here the asteroid is speeding up towards the Earth as the Earth pulls on it. The asteroid is about to crash into the Earth, going much, much faster than a speeding bullet, releasing unimaginable amounts of energy. So first we saw that air blast, and it's kicking up a bunch of rock and sulfur and dust into the air. Some 350 billion tons of sulfur went skyward from out of the ground. This ejected matter can stay up in the atmosphere, or it can fall back towards the Earth. 300 miles high above where the clouds form, a relatively thin layer of sulfur and dust accumulated. Since sulfur reacts strongly with water, it got trapped in the atmosphere. This dark cloud, not shown in the simulation, spread over the Earth in a matter of months and eventually caused this worldwide winter. This layer of dust would have stayed for decades, and meanwhile would have cooled the Earth by reflecting heat and blocking out the sun, thus halting photosynthesis for plants. Temperatures dropped by a full 35 degrees Fahrenheit during this period. For the particles that did fall back to Earth, they traveled through the atmosphere, turning falling energy into heat, so a lot of the objects went ablaze in the sky. This broiled the Earth's surfaces, plants and dinosaurs included. Herbivores big and small, especially the bigger ones, all over the world, died off due to lack of plant life to eat. And their predators died off too, because the herbivores weren't there to eat. Since the dinosaurs were large, they were hit harder than the smaller, hardier species. So when the base layer goes, everything goes. So with the layer of sulfur and dust blocking out the sun for years and years, plankton had very few tasty sun rays to make energy with. Without those planktons, the marine food web collapsed and a majority of ocean species went extinct. In order for this sulfur to return to the ground, the sulfur bound itself with water and fell down as acid rain, as seen in this picture. This changed ground geography and devastated shallow water marine habitats as well as land ecosystems. So a bunch of factors came together. Fires, volcanoes, earthquakes, all heated up the atmosphere to some degree. But due to the composition of elements in the area the asteroid hit, its immense size and speed, and the impact angle, the dominant effect was from the light blocking particles kicked up by the asteroid in the next month. This surely makes me wonder what it means to be evolutionarily fit. So while some scientists once thought that the dinosaurs may have perished due to volcanic eruptions kickstarted by the asteroid's impact, or maybe of a global plague, researchers now agree that dinosaurs and 75% of life on Earth eventually froze to death. This could turn out to be a blessing in disguise for our mammalian friends and ancestors, as it paved the way for a diversification of mammals.
All right, and I will be talking about that diversification of mammals. So the dinosaurs are now gone. What happens next? Without the massive extinction event that occurred, life as we know it today most likely would not exist. When the dinosaurs roamed the planet, they were the main predators, keeping mammals and other animal populations in check. As the dinosaurs died, they left large habitats and resources unused. This allowed for a great explosion of life and evolution to take place. The most prominent of these evolutionary effects was that of the mammals. As mentioned previously, mammals did exist during the time of the dinosaurs. They were very small and looked and acted more like reptiles. As the mammals had more space and resources, they began to change into what we think of mammals today. Some of the first adaptations that occurred is that their jaws began to change. Bones that reptiles used in their jaw moved to their ear, making it so mammals had better hearing. It also made space in the head so that larger brains could fit, and this would become very important as humans evolved. The moving of the jawbones also allowed for mammal jaws to slice and chew their food rather than swallowing food whole, as reptiles do, making it so mammals can enjoy a variety. Another important evolutionary change that occurred was the adaptation of mammary glands. Mammary glands most likely began as sweat glands on ancestral mammals. Both sweat and mammary glands produce water, salts, and proteins. The platypus is a great example of what early mammals most likely used to produce milk for their young. Platypuses don't have nipples that excrete milk, but have a region where milk ducts come together and the milk collects on hair, allowing the young to eat. So on the left, we see another basic animal phylogeny or family tree, which shows a reptile-like animal, which eventually adapts into the different types of mammals we see today. And here we see that platypus that I just described, which is a little bit more ancestral tending than what we normally think of a mammal, but it's still a mammal. And then something such as the Tasmanian wolf, which is what we think of as a real true mammal. And on the right, we have basically the same diagram, but just with bigger, fancier words that just show the long evolution of living mammals today. I also wanted to show just some basic pictures of what a mammal could have looked like back in the Jurassic period. So this is technically a mammal, but it's much more reptile-like. It doesn't have external ears, it doesn't have a good chewing jaw, so it doesn't really look like a mammal. But then this evolves into something like this next picture, which looks like a mammal we would see today. Lots of hair, external ears, and yeah, that's how they did. Moving on, we do see a big difference in number and body size happen after the Great Extinction event. So we see right at that orange line, we see an incredible drop of number of mammals. So mammals weren't all that lucky. They didn't get out scot-free. A lot of them did die in the extinction event. However, they were able to survive and continue to grow in both size and number as time moved on. So to answer my previously posed question, what happened after the dinosaurs were gone? The answer is lots of diversification. Arguably, one of the most important evolutionary changes that occurred to mammals is the formation of placenta. Placenta nourishes mammalian fetuses and protects the fetus from the mother's immune system by creating a physical barrier. Reptiles do this as well, but they create the physical barrier as an egg. However, reptiles cannot make highly developed young. Newborn reptiles are small. The creation placenta allowed for mammalian mothers to invest high amounts of energy and nutrients into their young, producing high quality, larger babies, but at lower numbers. Because of these and many other very important evolutionary changes, the mammals began to grow and diversify, filling up the niches or habitats that the dinosaurs once filled. The diversity and growth of mammals created a landscape like we see here, with lots of diversity, different shapes and sizes. And that diversity would eventually turn into the mammalian diversity we see today, like in the African plains. The mammals soon became more diverse than dinosaurs ever were. On this next slide, we can see just how diverse they became. They became large or they stayed small. mammals also went back into the water, as well as stayed dry on land. So here we're going to see a very ancestral whale swimming across the screen. So whales most likely look like this in their early stages rather than that, what we think of today. They had fur and not well-developed fins. That would come much later. It was also at this time that mammals took back to the sky. They grew wings and became adapted to live in that environment. It was this time of rapid evolution that we have to thank for our large brains and highly specialized bodies that we have. This photo shows an example of what scientists called adaptive radiation, which is just the idea that from one evolutionary event, lots of different animals can occur based on the different habitats and resources that they have available. So for example, a really ancestral small mammal can somehow evolve into a swimming seal or become very fast and agile, such as a cheetah. So it's just a really cool idea. And we did see this happening, and we see it happening today. Mammals were not the only thing that benefited greatly from the Cretaceous extinction. Reptiles at this time were also able to diversify and evolve. Smaller lizards could now survive and reproduce without the threat of becoming a dinosaur's dinner. Birds, or avian dinosaurs, also became more prominent. It is from these early avian dinosaurs that the birds outside your window evolved from. So here I show a picture of an early bird, which looks very much more dinosaur than bird to me, just with its talons and long legs. It's a little scary looking. And then on the left, we see an ancestral turtle shell. And I chose this picture just because of the really cool breastplate of the turtle. I think those spots are really interesting looking. They look like suns to me. But that's where turtles evolved from. So, the surprisingly happy ending. The Cretaceous extinction was bad news for the dinosaurs and much of the animals on the planet. However, it left this small number of animals that did survive the chance to grow and change, taking over the Earth. It was because of this massive extinction event that we see the incredible beauty and diversity that we see on Earth today, such as trees and animals, such as amphibians and fish and humans and marsupials and lizards and snakes. And it does say birds, but it doesn't really show anything about bird evolution. So I'm going to add one more slide about birds. And here we go. Here's the evolution of birds as told by a bird to another bird, just as I'm telling you guys today. Thank you.
So we have set the stage, met the characters. We saw the disaster strike, and we had the surprisingly happy ending. And that is our melodrama in 4 acts today. And I'm going to stop sharing so you can see our faces one more time, hopefully. Chris is roaming around the theater probably. And so that's our story. And we'll just sit here and see further instructions. We're hoping that maybe if there's any questions that we can hear them with Chris's help.
All right, I got it.
A little feedback in the theater. I don't see Chris anymore.
Yeah, I think he shut down his Zoom on his laptop. So I think he's just on his phone now. So I don't think we're hooked up to the main screen.
Yeah. So we'll just stand by for 10 minutes and see if anything happens.
Okay, sounds good.
Very good.
You too. Good
Very
job.
good. Yeah, everybody.
Yeah, we did good. Good timing too.
And we're still recording, by the way.
Okay, sounds good.
I think I will stop that.